So good morning, everybody. And what we are going to do in this lecture is to show which are the equations implemented in the Yellow code when doing a GW calculation. And this is mainly because of two reasons. First of all, in order to derive these equations, we will have an understanding of which are the approximations involved. And second of all, we will have an insight about which are the main convergence parameters that should be kept under control in order to have viable results. But let's start from what an output of a GW calculation is. So probably you will have done a DFT band structure or calculation of the band gap at the beginning, and probably all of you know what that means. Then in practice, let's say the GW is a correction or of the band gap, like in this case, where it can be seen that the calculated gap of GW is in better comparison with the experiment with respect to the LDA one, or you can have a full quasi-particle band structure. In this case, for graphene, we have a DFT band structure and a DFT corrected that is the GW band structure. Here, blue and red are two different flavors that will be covered in the next lecture. And hopefully, if you have an experiment, like in both cases, your GW calculation is in better agreement with the experiment than density functional theory one. So our goal is to calculate the band gap or the band structure, and we will understand how. So we start from adding these equations. These have been already covered, so I will go faster, but just to say that if you solve them consistently, you have the exact one particle green function. We'll suppose some of them are the quasi-particle energies, and then you can have your band structure at the many-body level. And the vertex corrections are very difficult to calculate. We can not consider them. And the self-energy is G times W, and this is the GW approximation. To remove the vertex correction also in the polarizability brings us instead to the random phase approximation. But actually, these now 4 equations, because equation 4 is trivially solved, must still be solved self-consistently. And this causes some complications, and there are other reasons, but in practice, what Yambo does is the so-called G0 W0 approximation, where both the G in the polarizability, thus in W, the screened interaction, and in the self-energy, are those of your starting point, that in our case is density functional theory. So what Yambo does when you compute a GW calculation is exactly to solve these 4 equations here. And the outline of my talk is to understand how these are implemented in the code, as I said before. But before I'm going to the equations, it is important to talk about basis set representation. All of these quantities here must be represented in a basis set in order to be numerically represented. And in Yambo, there are 2 different basis sets. The first one is plane waves, often called G-space, as in quantum espresso. And the second one is the basis of Kohn-Sham states, so density functional theory states, that is the output of quantum espresso, and at the same time, the input of Young. There are matrix elements that move from one Hilbert space to the other, and the reason why there are 2 Hilbert spaces is that because different operators can be conveniently represented in a different basis set. For example, the non-interacting green function is diagonal in the basis of Kohn-Sham states, and also the self-energy is we will approximate it as diagonal in the basis of Kohn-Sham states, while, for example, the tuberculum interaction is diagonal in G-space, while it depends on 4 Kohn-Sham indexes in Kohn-Sham states. So what Yambo does is actually to solve the screened interaction in G-space, then move to the Kohn-Sham space in order to calculate the self-energy. as we need in practice to truncate both Hilbert spaces, the first one with some energy E cat, as in quantum espresso, which provides you the G vector with highest modulus, while we also will use a finite number of bands in describing the Kohn-Sham Hilbert space. And due to the movement from one to the other, it is clear that these two convergence parameters are interconnected. And this is because if you enlarge the G space, you need also to enlarge the Kohn-Sham space in order not to lose the information moving from one to the other. So now we go to the Dyson equation for G. This is the Feynman representation, and this is the equation. Due to the Lyman representation, and to the fact that we are interested in quasi-particles, we can reformulate this and come back into an Hamiltonian formulation, where we have the Kohn-Sham Hamiltonian, that is the density function theory 1. The self-energy, we need to remove the exchange and correlation local potential and find these eigenvalues here that are the, let's say, GW eigenvalues. As we said, we are interested in the quasi-particle solution, and in particular, we are interested in the band structure. So in order to avoid this equation that is that requires a diagonalization, we can approximate the quasi-particle orbitals with the orbitals of density functional theory. By doing so, the Dyson equation becomes an equation self-consistent just for the quasi-particle energies that are our goal. And the self-consistency is due to the fact that we need to evaluate the self-energy at the quasi-particle energy. With the hypothesis that the DFT, that is this one, and quasi-particle energies are not too different one to the other, we can tailor expand the self-energy around the DFT energy. This is the so-called Newton method, and this will be the expression where we write the quasi-particle band structure as the density functional theory band structure plus a quasi-particle correction. These zeta factors, called renormalization factors, are linked to the quasi-particle approximation and tells you the weight of the quasi-particle approximation in the spectral function. And of course, it depends on the derivative of the self-energy with respect to the energy, due to the fact that we have done a Taylor expansion of the self-energy. Yambo calculates these renormalization factors by evaluating the self-energy at two different frequencies and then does finite difference method. Thus, in practice, what we want to do is to evaluate this equation that requires to evaluate the self-energy at two frequencies, and this will correct our density functional theory bands. But in order to evaluate the self-energy, we need the screening. And in order to calculate the screening, we need to start from the independent particle polarizability, which corresponds to the bubble diagram. I will not say too much about this expression, just that this is written in G space. And it requires a sum over theoretically an infinite number of conduction states and an integral over the Brillouin zone. Thus, in order to converge this calculation, we need to truncate this matrix in G space up to a finite element, sum over infinite number of states, and we will have a finite discretization of the Brillouin zone. And all of these parameters must be kept under control. This also because the calculation of the reducible polarizability is often the most time-consuming part of a GW calculation. This is because we need to sum over hundreds of states and perform this K integral for each element of the GG prime matrix, for each momentum transfer pool that is equal to the number of K points of your discretization, and for each frequency. Thus, in the next lecture, in the lecture Advanced Algorithms, it will explain how to try to reduce the number of calculation of the reducible polarizability, thus the screened interaction in the fewer number of points possible. Once we have one bubble, we need the geometrical series of all the bubbles. This is the random phase approximation. And Yambo does this by this matrix inversion, again in G space. There is not too much to say about that, but what is important is that once we have the reducible polarizability, we can obtain the inverse, the electric function, just by multiplying the Coulomb interaction, and finally, the screened interaction by multiplying with another Coulomb interaction. The screened interaction has been already discussed, is the interaction between two electrons of the system mediated by the presence of all the other electrons. Again, we have that all of these are matrices in G space. Then we need to compute these matrices. We need these matrices to be sufficiently large to describe properly the screening of our system. So in order to reduce the calculation, and in particular trying to evaluate the screening in less frequencies as possible, it is now common to perform this plasma pool approximation that again will be described in more detail in the next lecture. While in this approximation, it is first of all understood that the imaginary part of the screening, that is the imaginary part of the inverse electric function as a function of frequency, is proportional to the His signal, electron energy loss spectroscopy. And in a lot of practical crystals, the His signal is just dominated by the position of one plasmon. Then the idea is to model the frequency dependence of the screened interaction with this plasmon pole model. So with the hypothesis that there is just one plasmon with some residue R and some energy big omega. In order to get these values, we need to evaluate the screening in just 2 points and do an interpolation. This is done, it is important to note that this is done for each of the matrix elements GG prime and for each momentum transfer, while this reasoning in principle applies mainly for the macroscopic screening, so only for GG prime equals 0, but still the same procedure is applied also for microscopic screening due to computational convenience. So once we have the screening, what we need to do next is to calculate the self-energy. This is the Feynman diagram. We have an incoming electron which scatters with itself through W. And in the intermediate state, the electron, or the hole, exchanged some momentum and some frequency, some energy with the screening interaction while changing its band index. As in Feynman diagrams, we needed to sum over all different possibilities. This translates into the fact that the self-energy contains an integral over frequency, an integral over momentum transfer, and a sum over the intermediate states M. This multiplication is done in the Hilbert space of constant states, where the G0 is diagonal, and we need to move, as I said before, the screened interaction from the space of plane waves into the space of constant states with this matrix element that just change the base where you represent your operator. Next, it is convenient to split the screened interaction into 2 contributions. The first one is the bare Coulomb interaction, and the second one is the piece of the interaction which is caused by the interaction with all the other electrons. And as the self-energy is linear with respect to W, this corresponds to a splitting into 2 pieces of the self-energy. And we recognize that the first piece then is just the Hartree-Fock term, and the second term is some correlation energy, which gives you the difference between are trifocal in GW and contains the physics of the dielectric properties of the material. Due to this plasma Hall approximation and to the fact that the very interaction is energy independent, then these two integrals over frequency can be done analytically. And these are the final expression that Jambo actually calculates. It can be seen here that, of course, the correlation part of the self-energy depends on this plasma residue and plasma energy. That there are these matrix elements to change from one Hilbert space to the other, also here. And that again, we need to sum over a finite number of plane waves that must be converged. This again corresponds to a cutoff energy like in quantum espresso. We need to sum over a certain number of finite bands, M, which corresponds to allow the electron to excite up to a finite channel into this Feynman diagram. And we need to perform an integral over momentum transfer, which again translates into a grid where to compute the DFT orbitals in the Brillouin zone. Okay, so this is the summary. The G0 W0 in one slide. It seems there are a lot of equations, but this is just to recap. So we start from DFT calculation in quantum espresso, where we have the band structure, that is our starting point, and the Kohn-Sham, the DFT orbitals that we use to construct our Hilbert space. Then the G0 is diagonal in the basis of Kohn-Sham state. Then the first step is to calculate the screening in G space with these equations here. Then we need to evaluate the self-energy, both this X and C, with after computing the screening. And our final goal is to evaluate the self-energy at two different frequencies in order to calculate the quasi-particle correction, add it to the DFT, and hopefully reach a better agreement with experiments. So just to recap, we have seen the main approximation that are used in Jambo in a G0 W0 calculation. That is, first of all, the neglecting of vertex corrections. This brings us to the GW self-energy and RPA screening. We are not doing the self-consistency cycle of Bayes equations. This corresponds to the G0 W0. We use the same orbitals as density functional theory, thus we are interested only in the quasi-particle changes in the energies. We have applied the plasma Hall approximation in order to do the frequency integral of the self-energy in an efficient way, and then we solve the quasi-particle equation with this Newton method. So Taylor expanding the self-energy around the DFT eigenvalue. And the main convergence parameters, as we have seen, is this E cut, that is a cutoff in plane waves for what concerns the G space, again, as in your quantum espresso. So this is not the quantum espresso value, but this is just to say that it's like in quantum espresso that we have an energy that selects you a space of plane waves. We have a finite number of DFT bands included both in the calculation of the polarizability and the self-energy, and we have a finite Brillouin zone sampling in order to converge the integrals over momentum transfer. Okay, thank you.
Template for the approximation.
Yes, this is because there are two parameters in your model. So you model your frequency dependence this way, with this, well, okay, this A is probably equal to this R. I forgot, but just to say that you have a plasmon residue and energy position. So it's a two model parameter, then you need to evaluate the function 2 points and then interpolate.
Like, that's not a comment that considering the plasma for model, I still the literature is very confusing about since there are multiple models actually, and often in the papers we just read using the plasma for model. And indeed, if you look at different models, the accuracy is also can be also rather different. So I think that there is also some urgency to be very specific when writing papers about which model is actually being used. In particular, I think God believe that Ibex and Louis plasma flow models, they can be very different.
Yes, this is a technicality that I skipped in this presentation because it will be covered better in the next lecture, but actually there are different plasma flow models depending on the strategy of sampling or which sum rule you implement in order to find the position and residue of the plasma flow. Okay.
You asked about the remaining public conductor of the GW state. Is it that possible to have the and estimate the public conductor of the state and estimate the of the
Well, I'm not super sure that I understood the question, but I try. So are you talking about this approximation here? So the fact that you approximate quasi-particle orbitals with DFT orbitals. And actually, this is one of the trickier approximations, let's say, because it is not at all easy to understand at the beginning why, if this is just justified. And I also think that maybe in order to go beyond to this approximation is something quite advanced. I still don't know if there is in the stable version. I think Pedro Melo has done something about. Okay, but this is kind of a very used mainly because of numerical convenience, because otherwise you need to diagonalize this equation with the self-energy, and actually the shape of your orbitals are most of the time not your main goal. Your main goal are the band structure. Then you, with this approximation here, you move from the need to diagonalize a nonlinear eigenvalue problem to just evaluate the energies correctly. This is a really huge gain.
Can you tell about the PG, G-term kind? PG, G-term kind.
PG?
G-term kind. Plan using derivative calculation. PG. PG.
Sorry, can you?
He's probably asking clarification for the kinds of terminators that you can use in GW, which they don't provide.
Terminator. Okay. So, okay, maybe let me think about. Maybe this one, but so the point is that in the terminator, you use in general, you use only a finite number of, in this case, conduction bands. And then you are missing something that is the bands that are not included. So in these terminator strategies, you add some kind of pole or some kind of an approximate excitation that gives you the correct sum rule and which describes in an approximate way what happens at very high energies where the quality of your state is less important. So this is the maximum I can do without writing an equation. So if you want, we can discuss.
Anyway, it's explained in the paper of Brunel and Golf.
Yeah, but I think this is a summary of what happens.
I think also in the last Young paper, in the real sum equation.